Okay, the timer went off on me again, and I didn't quite catch that. But I think you've had enough time to understand that we go from A equal lambda, here A equals 5 times lambda, here A equals 10 times lambda. And so that the wider the slit, the narrower the central diffraction pattern. Okay, so wider slit here, this gets narrower. Okay, just to understand that way in which that works. Okay, let's check point number 2 here. This is the figure represents in a smoother form with more phasors. The phasor diagram of 2 points of a diffraction pattern that are on opposite sides of a certain diffraction minimum. Diffraction maximum. Which maximum is it? What's the approximate value of m, and that corresponds to this maximum? Okay, and so this would correspond to the second side maximum. And what happens is those are in between values, right? So it would be 2.5 on here, okay? Here's the checkpoint number 3. And here, this is 2 wavelengths. You've got 650 and 430 nanometers. Used separately in a single slit diffraction pattern, show the result of the intensity versus the angle theta, right, for 2 different diffraction patterns. If both wavelengths are used simultaneously, what color is seen in the combined diffraction patterns of angle A, that's this one, and then angle B. And you'll see that here, this is 0, and you've got something there. So that means for A, it's going to be the red one, right? And then the other one, you've got nothing here, and it's all that one, and so it is going to be the violet. Good grief. Okay. Anyway, so just can't control this thing. We're going to go on to practical exercise number 4. This is problem number 11 in your textbook. And here you've got a 0.1 millimeter wide slit. Wavelength is 589 nanometers. There's a point P at a viewing screen on a diffraction pattern of the slit is viewed. The point is at 30 degrees. This is your theta from the central axis. What is the phase difference? That's your delta phi, right? Between the Huygens wavelets arriving at point P from the top and the midpoint of the slit. And so this is equation 36.4. Delta phi is 2 pi lambda delta x, and this is the sine theta. Now here the alpha is 2 delta x, right? Your A value. Your A is 2x, 2 delta x. Okay? So 1 nanometer is 1 times 10 to the minus 9th meters. I don't know why they had to include that. We all know that. So delta phi is 2 pi lambda delta x sine theta. This is the equation that we just showed on the prior slide. So here the lambda is 589 times 10 to the minus 6 millimeters. Okay, and because we had the slit for the A value of 0.10 millimeters, and delta x is 2 of that. So delta x is going to be 1/2 of A sine, and then the angle that they gave you was 30 degrees. And so when you multiply this together, it turns out to be 266.7 radians, right? Now, it's 266 radians. Each radian is 6.23. There are 6.283 radians per complete cycle, right? So if you divide this by 6.283, the whole integer you're going to get is going to be 80. It's actually 42 pi. It's 42 cycles, or since pi is only 1/2 a cycle, it's 84 cycles. And what's left over is 0.447. 0.447 radians. Now 0.447 radians times the number of degrees per radian, which is 6.283. Okay, there are 57.3. Whoops, good grief. There are 57.3 degrees per radian. 57.3 degrees per radian, and that's how you get the 160 degrees here. Okay, so first what you do is you take out all the extra cycles that are complete, and that is this right here, and then this number right here is then multiplied by the factor of the conversion factor 57.3 to give you the number of degrees for the delta phi difference, the phase difference for this one. This is practical exercise number 5, and this is problem number 14. Here what we've got is light at 500 nanometers. Slit width is 6 microns. Okay, so this is and the viewing screen as the distance d equals 3 meters. The y-axis extends up from the viewing screen, origin to center, and here we're looking at intensities, right? Good grief. And at P, y equals 15 centimeters, right? So what is the ratio IP to IM? And so what we do is this is a sine alpha over alpha squared, right? That's what the equation is going to be for this. And determine where the point P is in the diffraction by giving the maximum and minimum between it lies, or the two minima between which it lies. Okay? So, given that y over d equals 15 over 30, so here what they did is they expressed that in centimeters, right? So it's 15 over 30 in terms of centimeters. Y equals 15 centimeters, and then you use d. Okay? So that means theta equals the inverse tangent of y over d, or 2.86 degrees. And alpha is a pi sine theta over lambda. A is 600 nanometers, right? That was the conversion that we had for the 6 microns. And this right here is already in nanometers. Okay? And so it's 600 nanometers there, 500 nanometers there. Sine of this angle right here times pi, that gives us the alpha value. That's 1.883 radians. So the sine alpha over alpha squared gives you this ratio of the intensities of 0.256. And that's the reason why they did this in terms of radians instead of degrees here, once they solved that. Okay, now we're back to our familiar equation from the first part. A sine theta equals m lambda. With a continuously variable m, of course m should be an integer for a diffraction minimum. For the moment we solve this as if it would be any real number. M equals a sine theta over lambda. And this right here turns out to be 0.6. When it's 0.6, that means that it's not, if it's at 1 would be the minimum, right? So it's away from the central angle, but before it gets to the actual first minimum. Okay? So it's between the central angle, the central one where it equals 0, and the first minimum. That's where this particular one is, right? Okay. Now we're going to talk about diffraction by a circular aperture. Diffraction by a circular aperture or lens with a diameter d, okay, that's going to be in this, so it's going to be this equation right here. And concentric maximum minima are given by sine theta 1.22 lambda over d for the first one. And then this angle here is this from the central angle to the axis for the first minimum of the single slit, right? Which locates the first minimum for a long, narrow slit of width A. The main difference is the factor 1.22, which enters because of the circular shape of the aperture. Okay? So this is a key difference. If you've got a circular aperture, you have to include this factor in there as well. Now, Rayleigh's criterion. This suggests that two objects are on the verge of resolvability if the central diffraction maximum is 1 for that. So you have the angular separation of 1.22 lambda over d. This turns out to be Rayleigh's criterion. If it has this, you can distinguish between them. This right here you can't distinguish. This you can't. This is somewhat. But this right here you can clearly distinguish between the two separate images. 2-point stars, right? If the angular separation is too small for them to distinguish, marginally and then clearly distinguished. And we're going to have some problems associated with how well you can resolve something. And remember, most of the telescopes and things that we have and our eyes are circular. And so our diffraction, for what we can pick out with our eyes, this Rayleigh's criterion tells you what you can resolve at what particular point. And yeah, they talk about it right here, pointillism. This is a type of art where essentially all it is just a whole lot of little different beads. And actually, when you talk about the newsprint of today, it consists of, and laser printers and all of that, those consist of all they are is just a whole lot of little different dots. And the dots, there are many of them for every single letter and everything that you have. But this right here is to make a whole picture of small colored dots. Is that when you change your distance from it, the colors shift in subtle but almost subconscious ways. And likewise, if you were to use a microscope on the newsprint, you would see some of the different, well, depending upon your magnification, it would determine the number of dots that you have making up that material. And that's how you can sometimes distinguish one type of printer from another type of printer, right? Okay, so suppose you can barely resolve two red dots because of the diffraction by the pupil of your eye. If we increase the general illumination around so that you can your pupil decreases in diameter, does the resolvability of the dots improve or diminish? Consider only diffraction. Okay, so what is happening here is you are increasing the light. Okay, so by increasing the light, what happens is it will diminish. It will not improve your ability to distinguish that. What you can do, though, and an interesting experiment, is when you look through something that has a whole lot of different individual little points in it. And so if you look through a type of a screen with a whole lot of different little points and put that in front of your eye, it's as good as if you were actually wearing glasses if you are nearsighted for some differences. But anyway, it's a interesting phenomena that you can experiment as they can see right here. But what effect does the light have versus not? So that your pupil, the reason why the additional light doesn't help you is because with the additional light, your pupil essentially decreases in diameter. Okay, this is practical exercise number 6. This is problem number 21. Estimate the linear separation of two objects on Mars that can be just resolved under ideal conditions by an observer on Earth using the naked eye. And then using a 200-inch, 5.1 meter Mount Palomar telescope. The distance to Mars is 8 times 10 to the 7th kilometers. Diameter of your pupil is 5.0 millimeters, and wavelength of light is 550 nanometers. Okay, so here what you're doing is you're doing theta r 1.22 lambda divided by d, right?